Greetings, salutations, all those nice things. Welcome to our first lesson in polynomial functions. We're going to be doing a little bit of analysis. We're going to be taking a look at some graphs that we've perhaps never seen before and kind of getting a feel for what these functions might do or how they might behave. As we get into it, we have this definition of polynomial functions, which if I knew how to zoom, would certainly be able to do. Oh, look at that, I can. So it's this whole thing here, which upon inspection looks like it's quite a doozy, but really it's not that bad. We've got these parameters that n has to be a whole number and that the coefficients are real numbers. So that means that we're going to see things like, well, any polynomial really. You could have like x to the 4 and maybe 5x to the 3 and like 0.2x squared and so on and so forth. Right? Anything that looks like a polynomial. Noting that all these exponents have to be whole numbers and that we have coefficients for each one of those powers of x. We have seen some of these things before. How does my eraser not work? There we go. For example, constant functions. A constant function you would have first been introduced to perhaps in grade 10 maybe? And that's where it's just a horizontal line. So y equals a is the general form of that. And it's just a horizontal line. This has a degree of 0. The highest exponent on the independent variable is 0. Right? You could say this is a times x to the 0, where x to the 0 is just the same thing as 1. So that's that. In a linear function, we've got degree 1 because the highest exponent on x is 1. And that could be something that perhaps goes like this. Maybe it goes from downland to upland, or maybe it goes the other way. Maybe it starts high and then goes low. So those are our degree 1 functions. We have also seen the polynomial functions that are based on quadratics. So the standard form of those is ax squared plus bx plus c. They are degree 2 because the degree of the polynomial corresponding to this is 2. That's of course because the highest exponent that we see on x is 2. What do these look like? They might go from up here to back up here. So maybe they go from up to up. Or maybe sometimes instead of the smiley face ones, we have the sad face ones. I could do something slightly more symmetrical than that. So those are quadratic functions, all ones that we've seen before. And there are other types of polynomial functions, and we'll be able to graph some of them by the end of this unit, such as cubic functions. These have degree 3, so the highest exponent on x is 3, and that's where you'll see something perhaps like this. A quartic function has degree of 4, and that's where we'll perhaps see something like that. And finally, a quintic function is where we'll see something that is maybe like this. Whoa! What a roller coaster. That's all sorts of fun. Whee! So there's some examples of polynomial functions. Now, in order to describe features of polynomial functions, we will need some definitions. Two very key ones are these here. So the degree of a polynomial function is the value of the highest exponent on the independent variable when the expression is in standard or simplified form. So we might see, like you've seen quadratic functions that are of this form, right? When that's expanded and simplified, it becomes one that where we can see the actual degree of 2. So right now, with the highest exponent we see on x is a 1 here and a 1 here, but that doesn't mean that this is a degree 1 function. This is not a linear function. So when it's in expanded, simplified form, that's when we can discern the degree. And that's how we'll get that. And it's the same as the degree of a polynomial in general, as you're familiar with finding. But again, just the highest exponent that we see essentially on x, assuming our function is based on x. The leading coefficient is the coefficient of that term that has the highest degree. So if we have a polynomial function of degree 5, we're looking at the coefficient of the term where x is to the power 5. Or if we have a polynomial function of degree 2, we're looking for the coefficient of x squared. That's what the leading coefficient is. And if this thing is in proper form or a standard form, then we're going to be arranging the terms by descending degree. Worth noting is that polynomial functions don't have any restrictions on the domains. So x could be any real number. We've seen this with quadratics, we've seen this with linear functions, and other polynomials are just the same. The only way you could have a restriction is if it was a contextual application and that context didn't allow for certain values. Like if it was someone diving off a diving board and they go off the board and into the water and then they come back up and resurface. Something like that, like the time before they actually dive, doesn't exist, so that's where you might have a contextual limitation. But any poops, let's display some using technology. So we don't know how to graph necessarily all these yet, but we'll just use that to help us. We'll sketch the shape here, and as we do so, we're going to note some things. So we're going to note the degree of the function, which we'll be able to get easily just from its equation. How many times each function changes direction, that might be how many bumps it has. There we're talking about, like, is it going up or down? That's the direction we're after. So if it switches from going up to going down, that's a change in direction. Or if it changes from going down to going up, that is a change in direction. And then whether each n moves toward a y value of infinity or negative infinity. So on the left side, what's the n doing? On the right side, what's the n doing? And then just where the y-intercept is. Those are the things we're going to tackle as we do this. So this first one is one that we are hopefully familiar with, but let's just see what it looks like. Okay, so it looks like that. We can draw that. So kind of like this. The degree of this function is 1. How many times does it change direction? When I look at this thing, as it starts, it's going up, and as it ends, it's doing the same thing. Like, it's going up the entire time. It never switches from going up to going down or anything like that. So this thing has 0 direction changes. The left end behavior. So over at this end, what is the trend that we're following? We can say that as x goes towards negative infinity, so as we go further and further left on this axis, what happens to y? Or f of x in this, it's just y. Y goes towards, well, it goes down, 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 so y is heading towards negative infinity as well. On the right side, over here, we're going to talk about what happens as x goes towards positive infinity. What does y do? Well, y is going up and up and up and up and up and up and up. So we can say that as x is approaching infinity, y is also approaching infinity. And finally, this y-intercept. The y-intercept here, according to this graph, is at 3. Done. All right, let's move on to the next one. Here we've got x squared plus 2x minus, oopsie daisy, minus 3. Oakley dokes. The degree of this one is 2. And, let's draw it on here. What color did I use? Still greenish? looks like we're going down here, and then we come up there. Okay. It's kind of generally what it looks like. Direction changes. Well, this function starts by going this way. As we move left to right, it's going down, and then later on, it's going up. So it changes direction once. So earlier it's moving down, then it moves up. On the left end, that's over here, as x goes towards negative infinity. Oops. Where's my negative? What does y do? Well, y is going up, 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 up. So y is approaching positive infinity. And on the right side, as we go further and further to the right, as x gets closer to infinity, what does y do? Well, y is going up, 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 up again. So y is still approaching positive infinity. Interesting, it's positive infinity for both of those. What an interesting little coincidence. And the y-intercept of this looks like we're at -3. There are 4 other graphs. I humbly ask that you give them a try, give them a go, see what information you get, and I'll put the same information here. You just make sure that we get the same stuff. Blah. Degree of this thing is 3. Here we've got x, sure, let's do it this way, cubed plus 2x squared minus 3x minus 1. I'm going to have to zoom in here a bit, I think, to really see what's going on. Okay. So it starts from down, and it's up here, and then it's down there. I can do better. Still. That'll work. How many times does it change direction? Well, it's going up, and then it's going down, and then it's going up again. So it changes direction twice. The left end is when x approaches negative infinity, so still on this left side here. As x becomes more and more negative, what happens to y? Well, y is going that way. So y is trending towards, whoa, negative infinity. On the right side, this is over here, as x gets larger and larger, so as x goes towards positive infinity, what happens to y? Y is exploding upward. So y approaches positive infinity. The y-intercept of this thing is -1. Let's type this one in. Up to the 4. Plus x squared plus 3x plus 1. Ooh, that looks exciting. Right? So it starts way up here. Okay. So it does something like that. The degree of this thing is 4. Direction changes. First it's going down, and then it's going up, and it's going down, and then it's going up. So as we move left to right, we encounter 3 direction changes. The left end behavior, so over here, as x is becoming super negative, as x approaches negative infinity, what's a good infinity? Y approaches positive infinity, because it's going up and up and up. It's just becoming more and more positive. And on the right side is where x is approaching positive infinity, right? We're going skyrocketing that way for x. Y is going up, up, up. So y is also approaching infinity. And the y-intercept here is at 1. This is interesting. I think the right-hand behavior has been that y approaches infinity each time. Huh. That's right end, y approaches infinity. Oh, right end, y approaches infinity. This is interesting. Right end, y approaches infinity. Wow, I guess for all polynomial functions, on the right end, y must approach infinity. I guess we could probably guess that for this one too, huh? Oh my goodness, we have something different. That came out of nowhere. I couldn't have predicted it. But here's what this one looks like, where we can see that the degree is 1, the number of direction changes is 0, and on the left side, as x approaches negative infinity, y approaches positive infinity, but it has different right-hand behavior from all the other 4. In this case, on the right side, y is approaching negative infinity. I really just didn't see that coming. Who knew? But we can still have the y-intercept here. Looks like that is equal to 4. Wow, that is so strange that the right side of this went negative when all the other ones were positive. I have no idea what could have caused that. Well, let's try this last one. Look, we got negative 2x squared plus 5x. Well, that's cute. Oh, so close. So close again. The perfectionist in me is saying that's okay. So the degree of this is 2, and we're looking at direction changes. It starts by going up and then it's going down, so there's 1 direction change. On the left side, which is as usual, as x is approaching negative infinity, in this case, y is going down. So y is approaching negative infinity. And on the right side, as x approaches infinity, y approaches negative infinity. Hey, that's just like our one on the left. So both of these ones had a right end that was going down. So weird. And the y-intercept is at 0. Thank you, Desmos, for helping us. We're going back to these notes now. So this is worth a little bit of analysis. We can look at a whole bunch of aspects of this. Let's start with the degree and the direction changes. In each of these cases, I mean, you can take a moment, pause, ask yourself what actually happens before I spoil it for you. But here we've got a degree of 1 and 0 direction changes. We've got degree of 2, 1 direction change. Degree of 3, 2 direction changes. Degree of 4 had 3 direction changes. And with the pattern we're noticing with each of these is that the number of direction changes is 1 less than the degree. Now, just so we're clear, it means that at most there will be that many direction changes. And these particular ones were chosen because they did have 1 less than that. But let's bring back Desmos that I so callously dismissed earlier. You could have a polynomial function like x to the 4, which actually only has 1 direction change. Right? It goes from down to up. But something that is quartic could potentially have more direction changes involved with it. Plus, oopsie daisies. Right, as soon as we start involving other pieces of this. Whoa, whoa, whoa. If we mess around with parts of this, then we can start seeing other direction changes happen. That thing's nuts. 9 is a big number. But at most, it could have 3 direction changes because its degree is 4. So that maximum number of direction changes is always 1 less than the degree. Next thing I want to look at isn't actually the end behavior, it's just the y-intercepts and how we can get that from this expanded form. So in this first one, y equals 3 is your intercept. And the second one, y equals negative 3, 0, y-intercept. Where does that come from? What's causing it? Also, what did I just erase? Because I think I pressed, undo too many times. Well, y-intercepts happen when x is equal to 0. When x is 0, every single term of the polynomial is going to be 0. So like in this case, like that's going to be 0, 0, 0, except for this constant. So that constant at the end is actually what tells us what the y-intercept is. That's the same thing as when you have something in slope-intercept form. The whole reason why this other piece was the intercept was because the other thing had the variable in it and didn't matter when x was equal to 0. So always that constant at the end in this standard form, and it's expanded and simplified, that's your intercept. Negative 3 in this case, negative 1 in this case, positive 1 in this case, and these last two we had a positive 4 and a 0, I guess. So that's worth noting. We do have some other stuff to do with left end behavior and right end behavior and how that is impacted by our function type. So let's do some analysis. Suppose we have a polynomial function of even degree, so degree 0 or degree 2 or degree 4. What can be said about the behavior of the function at its ends? So as x approaches positive or negative infinity, what can we say is happening? Take a moment, pause this video if you need to, but look at the ones that we had with even degree and see what you can get about it. What do you notice? What observations do you make? I'm going to spoil the surprise if I did this properly in 3, 2, 1. Oh, sweet. Look at that. So what we might have noticed is that if the leading coefficient is positive, then as x approaches either positive or negative infinity, f of x or y is approaching infinity. So we had these cases, right? This side, we were going up, both on the left and right. And this one, we were going up, both on the left and right. There was the other case, though, where we were going down on both the left and right sides, and that one had even degree. So if the leading coefficient is negative, then as x approaches either end, y is approaching negative infinity. But the big key for this is here. So if you have a polynomial function with even degree, the left and the right ends will behave similarly. They're going to be same. Now suppose we have a polynomial function of odd degree. What can you say about the end behavior of the function? Again, I ask you to pause the video, look at the graphs we have that have odd degree, and explore and hypothesize what you think is going to happen, or what we can say about the end behavior. What happens on the left and what happens on the right when we have an odd degree, because I am going to spoil it. If the leading coefficient is positive, f of x will go from negative infinity to positive infinity. And if the leading coefficient is negative, we're doing the opposite, from positive to negative. That's what we see here. So like this one goes from, oh, that's my eraser, undo, help me. We go from negative land up here to positive land. Same here happens. We go from negative land to positive land. And that's because in those cases we had a positive leading coefficient. In this other one, we go from positive land down to negative land. So sad. And that's because we have this negative leading coefficient. The key, though, in this case, is that if we have polynomial function of odd degree, the left and right ends will behave oppositely. So if one end is going up, the other end is going down. Next up, suppose we have a polynomial function with a positive leading coefficient. What can we say about the right end behavior of the function? So specifically just the right end. Again, look at the functions we graphed. Ask yourself what we can say. See if you can get the answer, because I reveal this in 3, 1, 0. As x approaches infinity, f of x approaches infinity as well. So if we have a positive leading coefficient, then on the right side of this function, we are going to be going up, up, up to infinity. If we have a polynomial function with a negative leading coefficient, what can we say about the right-hand behavior of the function? Take a look at those two examples with a negative lead. I might have spoiled this a little bit earlier. Maybe you remember that part. Maybe you're not listening to the audio and you're just trying to filling out the notes. I don't know. But take a look at them and ask what you can say about the right-hand behavior of the function. Well, I'm going to reveal it. Where's my eraser at? Skills. Woo! So as x approaches infinity, f of x approaches negative infinity. When we have a negative leading coefficient, then the right side of this function is going to go into super negative land. Final question is, suppose we have a polynomial function, f of x, that has degree n. How many x-intercepts could it have? And that's worth looking at our graphs again. But the answer is going to get revealed now, and that's n. It could have up to n x-intercepts. So like our linear function has only one. A quadratic one, you saw last year, it could have 0, or it could have 1, or it could have 2. But up to 2, no more than 2 for a quadratic function. And similarly, for a cubic function, it's going to have at least 1, but it could have 2, and it could also have 3. Right? Up to 3 when you have degree 3. And similarly for 4, you could have up to 4 x-intercepts. And if you have degree 5, up to 5 x-intercepts. That's all that business. Now we do have a couple examples to go through. Now we've done all this analysis, and there's quite a bit of analysis. So we can potentially identify information about graphs. So this question was just asking us, what do we know about this function? And we can get some of that information. So for example, we know that the left end approaches infinity. And we also know that the right end approaches negative infinity. So way up to positive infinity on the left, going to sad negative infinity on the right. That tells us that. And because the ends are approaching opposite directions, we know that this must have an odd degree. We can confirm that with our direction changes, because our direction changes should be at least one less than the degree of the function. So this starts by going down, and it's going up, it's going down, it's going up, it's going down. So 1, 2, 3, 4 direction changes. Which means that the degree must be at least 5. Has to be at least one more than the number of direction changes. Neat. We've also got a positive y-intercept. This also has 2 x-intercepts. Maybe that's useful, maybe it's not. Oh, sorry, 3. 3. I know how to count. It's my counting skills. 1, 2, and 3. If this was a little bit lower, then this area would go down. We could have 5 x-intercepts, but 3 it is. So that's all stuff that I think we know about this. And knowing that kind of information allows us to answer a question like this. So what's most likely to be the equation of this function over here? Which one would it be? We can do a whole bunch of analysis to this to figure this out. I encourage you to give this a try real quick before I dive into it and see what you get. Because here I go. I think that because these are going to the same end, must have an even degree. Which means it can't be this and it can't be that. The other thing is that since they're both going up, or at least since it's going up on the right side, that must mean that the leading coefficient is positive. Which means it can't be that. In theory, that means it's B. And just for another check, we've got a negative y-intercept, which that answer does have. So we're all good to go. That was a doozy of an intro lesson, but there is some practice work for you. Don't forget that as you do this practice work, not only should you be checking your answers, but you should be letting me know if you're running into any difficulty at all. So whether we are meeting in class or you're contacting me via Teams, find some way to make sure your concerns are heard. So please do practice that. Let me know how it goes. And if you have questions, comments, concerns, of course, please voice those. That is all for today. Ta-ta for now. Bye.